We ran a quick search about worldwide air quality problem. By searching for word combination, air pollution, and country and city, we found that China and Beijing ranked top 1 and 2 in terms of social sharing about air pollution problem, which means they are the hotspots of concerns. Then, this becomes one of the reasons why we decided to choose Beijing subway system as a starting point.
But can the Chinese government actually afford to tackle the Beijing air pollution by investing in this new application? By looking at data, it becomes evident that air quality of underground railway is of critical interest in Beijing, but also that the Ministry of Environmental Protection of the People's Republic of China has prioritized air pollution in its budget. Already in 2012, Beijing issued the first standard limiting particulate emissions from diesel fuel to reduce the PM 2.5 levels. Also, in 2014, they explicitly put efforts of reducing the congestion of trains as they drastically increased the price of train tickets from a flat rate of 3 RMB to pricing according to passengers' travel mileage. For example, the daily expense could go from 4 RMBs to about 20 RMBs. Without access to the actual budget, it is plausible anyway to assume that although they managed to decrease the number of passengers with 10%, in aggregate the price hike should significantly increase the resources for Beijing subway to employ more measures to improve the air quality in subways.
In an attempt to find the relevant patents in identifying the cutting-edge technology in air purification and filtration filters, I used the Quid Patent Analysis tool with the search query air purification and filters, which generated 346 patents. I first converted the network to timeline view to analyze the latest patents being filed or granted to find the cutting-edge technology. I then came across the exact patent I was looking for. This patent presents a specific activated carbon filter material useful for air conditioner filters. Because the status of the patent is currently still applied, and considering the date the application was filed, it is truly one of the cutting-edge technologies relevant to our scenario. Also, the original filing location is China, which is important as our application scenario is in China.
To clarify the calculations done in the activated carbon filter conclusion, I have gone into more detail here. We found that from the ResearchGate study, there were 2.49 times 10 to the power of 10 ultrafine particles, this is the below 0.1 microns in diameter size, per cubic meter in Beijing air, and that the volume of a Beijing subway carriage is 101.4 meters cubed. Multiplying these two together results in 2.52 times 10 to the power of 12. This is the number of ultrafine particles in Beijing air of the same volume as that of a subway carriage. We then needed to work out the average surface area of these particles. For the purposes of this presentation, we made the assumption that all particles are spherical and took 0.1 microns as the diameter of the particles for these calculations, just for simplification. Thus, using the equation for the surface area of a sphere, we found that the average surface area of one ultrafine particle is 3.14 times 10 to the power of minus 14 meters squared. Finally, multiplying this by the total number of ultrafine particles in this volume of air resulted in 0.079 meters squared as the total surface area of the particles. Due to the large number of pores created when the carbon is activated, we were also given that the surface area of activated carbon averages at about 1,000 meters per gram, and as there are 454 grams per pound, the average activated carbon surface area is 454,000 square meters per pound. Then, to conclude, we divided this number by 0.079 to give 5,746,835, which is the number of times that 1 pound of activated carbon can absorb ultrafine particles of the same volume size as a Beijing subway carriage.